right, video 2 of 10 people. This one will hopefully be short, talking about some relational properties we might care about. There's 4 properties I want to talk about. I'll name them all up front. I'll just go through them one by one, talking about a few examples. Okay, so first, we'll have reflexivity. Then we'll do symmetry. Then transitivity. These are all familiar relations. I want to add one to our discussion today called determinism. Okay, so I'm just going to go through each of these one by one. For the first 3, these really only talk about binary relations. That is to say, some relation are on a set. So that means a binary relation where they're both positions are talking about the same set, right? That's what we're talking about. Let me see if I can change the color of that. Ooh. Great. Okay. So let's look at some examples. Our fixed example sets for these binary relations. Here are our relations. We'll do equals, less than or equal to, and less than. All of these are relations on, well, a number of things, but we'll start with nat or nat, just because we've gotten the best intuition for that over the course, right? So we've got 3 relations here. We've got 3 relations here on the naturals. Okay, so let's see. So let's look at the first one, reflexivity. So for all A in the set A R A, i.e. A is in R. Everything is related to itself. That's what it means to be reflexive. Okay, so of these 3 relations, which are reflexive? Equal, yes, reflexive. Everything is equal to itself. That is to say, for all n is in the relation equals, or more clearly, n equals n. You know this from the cock tactic, reflexivity. Okay, what about less than or equal to? Is everything less than or equal to itself? Yes, you bet. For all n is less than or equal to n. Okie dokie. What about less than? No. Excuse me. No, less than is not reflexive. Why? There does not exist any n such that n is less than n. There's none of these. Okay, let's look at symmetry. Okay, symmetry says you can mirror image the relation. For all A, B in A R, B implies B R, A. Let me write that a little more neatly. That is to say, A, B in R implies B, A is in R. Okay, what's the status for each of our different relations? Well, equals. So is it the case that if A equals B, then B equals A? Yes. A equals B implies B equals A. You bet. What about less than or equal to? So is it always the case, right? Is it always the case that if A is less than or equal to B, then B is less than or equal to A? Well, it's sometimes the case. Right? Only for certain A and B. Right? In particular, only when A and B are equal. So we're going to write an X because sometimes is not good enough. Right? For a relation to be symmetric, it has to always be true. Right? It needs to be all A and B. And here, it's just not the case that that's true for all A and B. Only some of them. Okay. Last case. Is less than symmetric? No, never. Right? It's never the case that n is less than m and m is less than n. Like, what crazy world are you talking about? I'm going to even draw a lightning bolt. I'm just that upset. Okay, last example. Let's look at transitivity. For all A, B, C in A, put some commas in there. If A is related to B and B is related to C, then A is related to C. Okay. Which of these relations have this property? Does equal have it? Yes, absolutely. We've even proved a lemma equitrans, right? It's of course the case that equality is transitive. What about less than or equal to? If n is less than or equal to m, whoops, that's terrible handwriting. If n is less than or equal to m and m is less than or equal to o, is n less than or equal to o? Yes! We proved this in cock. So it's really got to be true. Draw slightly better less than or equal to. Okay, what about less than? Well, is n less than m and then m less than o? Does that mean that n is strictly less than o? Yes, absolutely. In fact, you can get this using the same lemma based on how we define things in cock, but it's also just generally true. Okay, so to zoom out, quite literally, we can see that equals and less than or equal to are both reflexive. Only equals is symmetric, and then all three of these relations are transitive. Okay, there are tons of other relational properties that people care about, but these are the sort of the biggest three, I would say. Okay, lastly, let's talk about determinism. Okay, determinism. Determinism, I'm going to show you for a binary relation, but it can actually be defined for any relation that has two or more places. So determinism says for all A, B, and C, if A are B and A are C, well, that means that B has to be equal to C. Why is it called determinism? Let's think about this definition for a minute. I'll write it another way. So AB is in R, and whoops, that's the wrong thing. And AC is in R implies B equals C. What does this mean? So here's a translation. Each left-hand side relates to only one thing. It's determined rather than indeterminate. Okay, so determinism. So let's think for a second. Are any of the relations we've looked at so far, right? Equals, less than or equal to, less than. Are any of these deterministic? Well, is less than deterministic? No. So let's do them in order. So less than, well, we can have 0 is less than 1 and 0 is less than 2. Not the case. By the same token, 0 is less than or equal to 1, 0 is less than or equal to 2, not the case. Okay. But 0 equals 0. What else can we, well, the only thing we can find it equal to is itself. So yeah, the equals relation here is deterministic. Okay, and a preview of what we'll talk about 2 videos from now, I want to define one more relation. Here's a relation S. I'm not going to say what it means, but I'm just going to write it down in set builder notation. S is equal to the relation n S of n for every n in the natural numbers. That is, for all n in the natural numbers, and S of n is in S, right? The type S is a subset of naturals times naturals. Okay, and this relation S is deterministic. Okay, cool. That's it for now. One more video just on some relational operations, things we can do with relations, and then we'll move on. We'll start talking about functions, and after that, we'll talk about countability. Take care, everybody.